Alright, this video we're going to take a look at the color mixing and intensity on these WS2812 serial LEDs. We're going to use the same circuit board here as we had for the timing tests. And what we're going to do is add a hex keypad. And this is one that's available just about anywhere. I've seen it on Jameco and DigiKey, and I'm sure you can get it various other places. It's a pretty nice, just a 4x4 matrix, like most hex keypads. The feature of this one is it has a little more functionality to it. Of course, you have to provide all this extra functionality by software. It doesn't come free or anything, but they've got the graphics on here that allows you to do some neat stuff, and it saves and it gives you more functions than what you could have on a regular 0 through F hex keypad. So what they've done basically to get the extra functionality is to have a second key here, and in orange you can enter your A, B, C, D, E, F. I don't know if you can see, it's in orange in the corner of 1 through 6. You get A through F, so that saves 6 keys there. And you also have a second function with up and down. You have left and right, and you probably can't see those at all. Now you also have clear, help, and enter. And the back of this guy is just a 9-pin pin connector. It's got ground, which probably, I think ground comes in right here on this tab, and I think it probably grounds the mechanical buttons on the top side, so you don't have any static coming through or anything like that. And the other 8 pins are the 4-row and the 4-column, just standard hex keypad stuff. And we're going to be using this for directly entering our color data into our LEDs, so we can do our color mixing test. Okay, let's have a quick look at the schematic for our serial LEDs. For display, we've got the serial display NHD. All we need is the transmit connection from the PIC, which is RC6, no receive. Then the LEDs themselves, we have data in. First guy puts his data out, and the second LED is data in. We have VDD and ground. VCC is filtered as per the spec, and I believe VCC is for the logic chip inside, and VDD is actually the LED supply. That's what I'm guessing anyway. We have the keypad. We drive out on row 1, 2, 3, 4, port B, and we get our data back on column 1, 2, 3, and 4. There's internal pull-ups we have enabled on port B, and that makes it nice. We don't have to have any external pull-up resistors on the board. I have a regulator on here, but I've never implemented this. Everything on here is 5 volts. The LEDs are 5 volts. I did this early on when the spec mentioned 6 to 7 volts for power, but that's apparently not required. I left it on here just as a note for in the future if I forget all about it. I'll have it on here as a reminder. And that's it for the schematic. So let's look at the code real quick. Okay, let's take a quick look at the code, and you can see maybe that it's in C. I know all you C guys are happy about that. This is my first real project in C on a microcontroller. Learned some things along the way. This of course is for the 16F886, and it was done in MPLABX version 1.9, so I'm kind of behind on my version. First I defined some type values that I use a lot.
so we don't have to type out all these long strings and just type register, const, or byte. Here's the GPR definitions. These mostly take care of LCD and LED data. The LED color registers are here. They are in order of green, red, blue, LED 1, LED 2. I got a structure here for some of the keypad functions. Here's some defines for cursor position, defines for LCD commands, some debug, function prototypes. I don't think these are necessary because I had left one out and the compiler never complained, but it was one without any arguments in being passed, and it was void. I'm not sure if you can leave those out and you need the ones that have arguments. I'll have to figure that out. New configuration word I had to understand for the 886, so I wrote it all out. There's the pragma for the bits. Main's really simple. I call the initialization enter into a while loop that runs forever, and it just calls keyboard scan and the keyboard decode, and decode handles going to calling all the functions. So this is all we need for main. Now sysinit right here, I think you're supposed to initialize the system before main is ever called, and they have a special function that you link to, but I found that out after I got this working, and sysinit was a little hard to get working because it seemed something seemed to be sequence dependent. I'll figure out what you're supposed to do here for initialization and do it next time. Since this is working, I'm just leaving it alone. Here's some new registers for this chip that I made some ASCII art for. Here's the initialization, all your registers getting set up. The transmit color routine just sends the data to the LEDs, and it is in assembly because C will not go fast enough to do this. You have to meet the strict timing that we looked at last time, and C's just not going to cut it. It's pretty straightforward. Here's your keyboard scan. Basically, we want to turn the keyboard scan into a number from 1 to 16. That's done by taking our row and column, modifying them, modifying column to 0 through 4, and the row count essentially, which indexes into these drive characters for port B that drive our rows. Row count gets modified to a value of 0, 4, 8, or 12. Those are added together to get 0 through 15, and then we add 1. So a hit on the keypad is 1 through 16. If it doesn't get hit, key press raw is 0. And in the key decode, that's what we check for right away, is key press raw being 0. If it is, there's nothing to decode, so we just return. We also start out with ASCII character cleared to 0. Then we go through our switch statement, which looks at raw, which is 1 through 16, so all the cases are just 1 through 16. There's a second function on this keypad. Here we test it. It's kept in key press second. If it's not set, the first key is the 1. We put a 1 character in ASCII and a 1 binary in raw. If the second function is set, well, the second function for this key is the A, so we put the A character in ASCII and a 10 in raw. 2 and 3, same situation. The fourth key on this row is up, or second function of left. So here we do roll up or roll left. Next row is 4, 5, 6, and they have the second function of DEF. Last key on this row is the down or right. So we call down, or the second function of right. The next row, 7, 8, 9. Straightforward, no second functions. And here is the second key. For the second key, we just set key press second to 1. It's true, that's all we have to do. We're done. We wait for the next key. 13 is the clear, so we call clear. Hit the zeros here at case 14. The help function at 15 and the enter. And we default. If something went wrong, we got a number greater than 16, we don't know what to do with it, so we clear raw and ASCII, and that causes no effect on a bad number. Now if ASCII is something, if it's greater than 0, we have a ASCII character that's going to the color data and to the display. So we have to handle both those situations. So real quickly, we this offset is set to 3. If we're on LED line 2, it's cleared if we're on LED line 1. Let me show you how the LED is laid out. The LCD is laid out, rather. There's 2 lines, basically, where we enter our data. This is first line's LED 1, second line's LED 2. We have green, 2 nibbles for green, then red, then 2 nibbles for blue. Same thing on line 2 for LED 2, green, red, and blue. And we've got a little space in between to make it look neat. These are the cursor addresses. You see on line 1, bit 6 is set for every position, the 4 hex. And for line 2, bit 6 is never set. So that's how we differentiate line 1 and line 2. That's what's happening here. We're putting the offset 0 for line 1 and 3, since there's 3 LEDs for line 2. This is the address of the first GPR that holds color data, and here's our offset we just calculated. Now nibble are these values for these positions on. It's the same for both lines 1 and 2. It's 0 and 1, 2, 3, and 4 and 5. And you can see that nibble is even for the most significant nibbles, and it's odd for the least significant nibbles. So here we divide nibble by 2 essentially. We make it even, and that makes it actually the full byte pointer. So with our address, offset for the line, and which byte we're on, that's the address of the register that this ASCII data is going into. So this FSR is used for indirect addressing, and whatever address is in here, when you do INDF, it uses this address. So we read that register and put it in color. Now our nibble, to find out if we're in the most significant or least significant bit, we just test it for odd or even, like I just pointed out. The color value gets modified with the new ASCII data. Most significant bit here, least significant bit here. We write it back to the register now that we've fixed it. We put that on the display. The ASCII character goes to the display, and we roll the cursor right. This just does some housekeeping. This is essentially the same function as the roll right, as the right key, but it keeps track of our cursor and nibble positions. Here for key press raw equal 12, that's the second function. If it has not just been set in this pass, it gets cleared all the time, so it doesn't hang around. And here we debounce the key release. Roll up consists of finding out what line we're on. Here's our bit 6 test for line 1. If we're on line 1, well, we make it line 2. Nibble goes to 0, and we send that cursor position command to the LCD. And this is the case with line 2. Set the cursor position to line 1 and send that to the LCD. Roll down is we just call roll up. Since there's only 2 lines, it can only go back and forth, so rolling up is as good as rolling down. Here we have a roll right. Now this is a little bit tricky. If you're new to C or haven't used switch statements a whole lot, you might not realize that for a case statement you can have multiple case statements at one entry point. So here we have 2 case statements to enter here. Either the cursor position is 1A or 4-6. And so if it's either one of those, you enter the code here and run down to the break. Same for here. If you have 1D or if you have 4-9, you enter here and run down to the break. And 20 and 4C. Now, the other thing is when you do enter, you don't, the case statements no longer affect you at all, so you just start the code here and you keep running no matter what until the break. Case statements out here have no effect on if you've already entered the flow of the code. So a case statement's not limited to one case per set of code in a break. It's pretty flexible this way. So what we're doing here is finding out how to move the cursor to the next position on the display. If you look at, we remember 4-6, 4-9, 4C, and here we have 4-6, 4-9, 4C. Now what's similar about those? Why are they grouped together? Well, they're the most significant nibbles of each of the words. So we're going to can treat them pretty much the same. We're moving the cursor one position to the right, and we have to keep track of what nibble should be. For this case, it should be 1. In this case, it's going to 3. In this case, nibble's going to go to 5. So if we look back here at the code again, we see here's our nibble case should be 1, 3, and 5. And the way we do that is we enter here for the most significant nibble. We have nibble set to 5. We subtract 2. Then we go down the next instruction, subtract 2 again. So that's a total of 4. Nibble is 1 for this entry point. And we add 1 to the cursor and a break. And that's it for that position. For 1D and 4-9, we just subtract 2 from 5 to get a nibble value of 3. Add 1 to the cursor and break. And for 20 and 4C, nibble is already 5. So we just have to bump the cursor and break. Now we have another group of 2 on 2 different lines. 4-7, 4A. Let's look at that. 4-7, 4A. What's unique about these? They're the least significant nibbles. Except we don't include 4D because he's the last guy on the line. The cursor has to wrap around, so that's a unique case. So for 4-7 and 4A, also 1B and 1E, we want to move the cursor position 1, 2 positions and end up with a nibble of 2 or 4. So here, if we enter here at 4-7 or 1B, we subtract 2 from nibble, that gives us 3. We subtract 1 more, that gives us 4. So that satisfies a nibble for 4. The 1E and 4A, we just, we get a nibble of 2. We subtract 2 and subtract 1. Bump the cursor twice and break, and that gives you a nibble of 2, and a cursor advanced by 2. If you enter here, subtract 1 from nibble, gives us a nibble of 4, and bump the cursor twice and break. And this is the guy on the end. He's unique by himself. He's going back to the first character on the line. So nibble is 0, cursor position is -7. Puts it all the way back to the starting position. Row left is the same thing, same idea except going the other way. You can use what you know from the row right discussion to figure that out. Clear blanks the data line and the data, and puts the cursor at the starting position for line 1 or line 2. Help, there's no help, so we just return. The enter key, this actually sends the data and puts the cursor on the first line of the current line. So for on line 1, we go to the L1 cursor position, that's the starting address. Else it's line 2, we go to L2 starting position. Nibble goes to 0 because we're going to the first cursor position. We transmit that cursor position to the LCD, and we send the color data to the LED. These are just the LCD commands that send data or command to the LCD. And here's some a function sends a string in memory to the LCD, and the prompt just calls that display routine with the initialization. And then there's a delay. It's just 3 separate for loops that handle our delays. And that's pretty much all there is to the code.
Okay, we've got our hex keypad connected here. Kind of a iffy ribbon cable connection stuck on port B of the PIC. And we got our little display with our prompt and our LED data entry lines. This is gonna, I was planning a longer demo than what this is gonna be. You've probably seen on other LED videos that photographing these things is really difficult. And I was gonna demonstrate about 3 different color combinations, but I'm just gonna do one. Basically, so you get the idea. It's not going to really come across that well because of the photography. Really bums me out about that, but sorry about it. We'll do the best we can. We'll get the hopefully we get the concept across of what's going on here. So basically, on our circuit here, we can punch in values for any color combination we want. Let's just put a 10 hex on green for LED 1 and enter that. And there's our green LED. And go down to the second line, step over to red, we'll put a 1 in on that and enter that. And there's our green and red. And let me kill the light here. So there's our green, red bits we put in. I've got this on nighttime setting. It looks like the display used to blank out, just white out completely, but it looks like the nighttime settings help. Maybe we'll get some fairly good color color response out of this thing. We'll just have to see how it goes. Okay, now I'm going to clear. Now the trouble is with the light off, I cannot see my keyboard at all. So I'm going to clear those, or I'll just go ahead and put. We're going to start with kind of an amber, a 60, 80, and go up to the top line and clear that. And enter. Now that's a bright, and that will usually do in the thing. It's holding up pretty well. There's a bright, it's a yellow. That's the trouble, the color gets washed out. That's really kind of a yellowish amber color. Well, it just about looks practically white. So anyway, what we're going to do is is adjust our intensity. We want to make an intensity that's half that. So on line 1, if I half of 60, if I put in 30, and then for the 80 hex on the red, I'm going to put in 40, half of the 80, and we'll enter that in. And it's supposed to be half the brightness, and it looks a little bit less bright, but that's not half the brightness. So what's the problem? Well, the problem is called gamma correction, and what it is, your eyes do not respond to the light the way in a linear fashion. It responds in a logarithmic fashion. Then gamma correction will correct this. So we have a table of values that are commonly used to do this correction. So if you want a half brightness, you use the table adjustment. And I'm putting up a link to a good website that has a little bit of discussion about this and a table. And later on I'll introduce some Python code that that lets you generate these tables and for your use. So anyway, let's look at the gamma correction table and see what we should do in this case. Okay, here's our gamma correction table. It's exactly like the one that I linked in on the website. This version, all values are in hex, of course. And what we have here is all the indexes listed in order: 0, 1, 2, 3, all the way up, FE, FF, and what their values are in hex in the table. So we see a string of zeros at the beginning for our value, and it's just like it is in the 2.8 correction table on the website. It's exactly the same table, just rewritten. So we want to look up the values that we're using on our breadboard. So what I punched in originally was a 60 hex for green and an 80 hex for red. Now we have to assume, now that I just pulled those out of the air because I knew it was about half bright, wouldn't destroy the camera exposure completely, and so that's where those numbers came from. They're just picked out of the air. Now we have to imagine that those were selected by this conversion table. So we have to kind of work backwards and see what's green 60. If that was our conversion table result, what were we putting in? So let's look for 60 hex as the result, and right here, and we see that was B4. So we're pretending that we use this table and we set our color to B4, and it actually generated the 60 we have on the screen. Now we want to half the intensity. So the value we're going to half is this, the entry, the index into the table. So half of B4 is 3A. Well, I'm sorry, it's 5A. No, I'm wrong. 5A. 5A is 0E. So that's what we should punch in on the keypad and put into our breadboard. 0E for green. Now we need to do the same thing for red. You need to look for 80. Well, there is no 80. There's 7F, and it jumps to 81 because this table is not linear, of course. So let's use C8 as being the closest. Difference between C7 C8 is going to be really negligible. So so if you take half of C8, we get 6.4. So let's look up 6.4. It's 1.3 hex, and that's what we want to enter for red. on our breadboard. So let's go do that and see what happens. Okay, so let's enter our codes we just figured out into here. So for the 60 value, that's going to translate to 0E. And for the 80 value, that's going to translate to 1,3. And now this should look like half. The first LED on the right should look like half the brightness of the LED on the left. And that is more like it. And the color, although you can't tell, it may have drifted slightly more to the red. The thing I've noticed when you reduce the intensity of these LEDs, you can pick out the individual LEDs better. They don't mix, since it's a very clear lens over these LEDs. So sometimes you can see more of one color than maybe is actually available, because you can pick out the individual LEDs somewhat. But that's a pretty good color match, and half the brightness. I guess I can't fiddle too much saying that's half as bright as the other. It's kind of hard for me to tell. I don't have a meter or anything, luminosity meter. It's kind of a subjective judgment without an instrument to actually do the measurement. But I would buy that as being better than our original half step, dividing the X values just in half. That clearly was not half brightness to the eye. One thing, how about if we step down a quarter and see what happens to try to get our half brightness. So 60 would have been 3 1/8. And a quarter of 80 would have been 4/2/20. See how that comes out. This is a linear reduction, and so that's a quarter of the original value, and it does look about half bright. Maybe it's a little brighter. It is a little brighter than the previous one, but it definitely has more red in it. So the color is changing. And that's another thing you might do with these tables. If you want to play around with these tables, you might generate a little different table for individual colors. So anyhow, that's the way gamma tables work, and it looks like they work pretty well. Okay, so like I mentioned earlier, I wrote a Python utility that'll generate any gamma correction table you'd like, and this is basically an adaptation of a processing program at this website here that I've linked in previously. Processing, I'm not sure. I've never heard of that. At a quick glance, it looks like C. I don't know why we need another new language to do some little task. There's a lot of people out there that like writing new languages. So anyway, everybody on Linux has Python, so you don't have to install anything. You just can run this script. Like I say, the adaptation is basically this line here. This is the formula that generates the gamma numbers. All I've added and changed was the ability to enter an argument, and that argument's in the shape of a floating point variable of single digits. So this the original value was for the correction factor was 2.8. So all I have to do is type in 2.8 as the argument, or you can type in anything else if you want to try out different tables. And
And the stuff here is just testing to basically verify that you've entered a good correction factor. Otherwise, it's just about exactly like the processing program. One thing it does, it makes an output file name based on your input, or excuse me, it makes an output file name based on the number, the correction factor you put in. So the output file name is going to be gamma underscore your correction factor .tbl. You guys on Windows might have to change this to txt, since Windows figures out what files are by their extension, but Linux have no trouble with that. So basically you run that and it generates a table that looks like, if I can find the thing, that looks like this. You can just cut and paste this into an array in whatever language you're using, and probably any C driver for your LEDs. You can just paste it in and use the value you want to put in. Use that as an index into this table, and use the actual value out to send to your LED. And there's also a program that will turn this into what we looked at earlier, into our hex file, and this is for human use. If you want to manually look up the numbers, it's got the all the offsets are first, the indexes into the table are first, and then the value that you've generated. So you can use this for manual functions like we did in earlier in the video. So that's basically it. Those two programs, the generator and the conversion to this, both of them are included in the downloads, along with the C driver for the hex key and the LEDs, and the schematic is all, a PDF of the schematic is also included. Okay, we're going to take a look at our signal here a little bit. If you saw the previous video on this about the timing, we found that we could generate a bit times that fell within the spec. For 0 bit time, we were high right out to 500 nanoseconds, which is the max. And for the low, we were, I think, 850 or 750, I forget which. I think it was 850. And for the high bit, we were 750 nanoseconds, which is great, and we were about I think 500 nanoseconds here for the low period on a 1. So anyway, that worked great. We generated that code by writing it inline. In other words, it was either a bit set, a bit clear, or a no-op. We just went straight through 48 bits, no calculations, no figuring out bit count, no figuring out LED count, no figuring out what address you're on. It was just straight through, and it met this spec perfectly. And from that from that pattern, we determined that by putting in delays, we determined that you could get away with a lot more than this low time, and in either case, either 0 or 1. In fact, we found it was about 6.8 microseconds, so 6,800 nanoseconds. Pretty good amount of time, 20-something instructions. So we want to see how we're doing now that we have to count color registers, count 8 bits, do shifts, count when we're done, and all kinds of overhead processing like that. And we do all that processing during the low time, and we have to beat 6,800 nanoseconds. So here is a write to 2 LEDs. I've got 5.5 in the red for LED 2, and so we got his red turned on, and we can get a set of 0 and 1s here to look at. Now let's look at
the timing in between 2 bits, because we're taking, well, first let's look at the timing of a single low bit. Here we're 200 nanoseconds. That's 500 nanoseconds. That's exactly what we generated during the test. But for the load time, however, we have extended it out to 2, 4, 6, 8, 10, 12, 14, 1500 nanoseconds. So that's not using a whole lot of that 6800 nanoseconds. 1500 isn't much at all. So between bits, that's doing pretty good. I'm doing real good. Now let's look between color bytes. Starting from this low, we have 5, 10, 15, 20, 25, 30, 35, 35, 37, 50 nanoseconds. That's about half of our 6800, or a little, maybe a tad more. So we're using a pretty good amount of time there. That's probably our worst case. In between, we got to calculate. We're turning around. We finished counting a bit, so we got to reset the counter. We have to go address another byte. We have to get that byte in. We have to set up our 8-bit counter to start counting 8 bits again. So there's a pretty good amount going on there, and we only used up about half our allotment. So we got a lot of margin. We might even be able to do a few more things. The bit between, in this case, there's no, the bit between color or LEDs is going to be the same, because this is linear. There's nothing else going on. There's no other thing to keep track of. It just goes through 6 registers in a row. So all the gaps are going to be that 3750. Let's look down here and see how 1 bit did. Look in our 1-bit data. And there's a 1 right there. And he's going to be 2, 4, 6, 8. That's 750 nanoseconds. And that's exactly 750 nanoseconds is exactly where we were right there, and that's in spec. And the load time on that is probably going to be identical. I don't see why. Whoops. Get back there. It's probably going to be identical. 200 nanoseconds, 2, 4, 6, 8, 1,000, 1250, 1250 nanoseconds. Seems to be a cycle missing, wasn't it? It was like 250 or 500 nanoseconds greater. I forget. Here's a 1. So wait, what was it? 2, 4, 6, 8, 10, 2, 4, 14, almost 5. That's 1500 nanoseconds. Two, 4, 6, 8, 10, 12. Yeah, it's the same. It's the same. So there you go. Oh, and one other thing I wanted to look at is this is data coming out. This is curious. I'm putting in 1, 2, it's 100 nanoseconds. 1, 2, 3, 4, 500 nanoseconds. Coming out of the guy is 1, 2, 3, 400 nanoseconds. He's shortening it up a little bit. Doing the retransmission, he's like right in there at 350 nanoseconds. So he's shortened it up a little bit for us. That shows you the jitter you can have in the spec. And Where's the data? Where's the one? 246 750 2468. Stretched it a little. Stretched it on the high bit right to 800 nanoseconds. He's closer than we are. Well, still in spec. And I imagine different parts might do a little bit different. So anyway, that's the timing. So our routine's well within timing requirements. Alright, I've decided to do one more color demonstration since the camera seems to be working pretty well on the nighttime setting, and at least it's a lot better than it was when I first started playing around with it. But this time we're going to make kind of a rose color, and we're going to use the same hex values that we entered for the amber color. And so in this case we don't need to go back to our table and look up values. We just use the same gamma correction values that we figured out from the previous one. So here I've got hex 60 on red, hex 80 on blue. Enter that, we get kind of a rose, kind of a pretty color. It doesn't really look a whole lot like rose on the camera, but it's a lot closer than it used to be. It's okay. We'll real quickly we'll try to half it linearly like we did before. Go up to the top screen. So half of 60, of course, is 30, and half of 80 is 40 hex. And we'll look at that, and there it's not half, not near half the luminosity. The color's pretty much right on though. Let's go to quarter that, and we can get kind of close to half intensity we saw before, and half of 30 is 1/8, and half of 40 hex is 20 hex, and we'll enter that, and there it may be half, but the color is definitely more towards red than it was. Let's try our intensity values, gamma corrected. Half of the gamma correction is, what did we use for 60? We used 0E, 0E, and 1/3. And there the color, the shade's more consistent, and it is about half the brightness, I suppose. Once again, it's a little bit subjective. But anyway, that's another demonstration of the gamma table and what it does for you. If you don't care too much about color, you're just showing bright colors, you probably don't ever need it. But if your application includes like fading one color in or fading the color out, to maintain your color and control your brightness in a linear fashion, the way your eyes work, you need to use the gamma correction table. Okay, one thing about using this hex keypad, a lot of people have used potentiometers, 3 potentiometers to change the color values, and that's a neat idea. But I went with the hex keypad in this case because you can enter a value and then watch your LED change, watch it pop and to your next color or brightness level or whatever you're looking for, and you can compare it a lot easier, it seems to me. Changes like that. With pots you have to remember what it looked like and dial up the new color. But pots have definitely have a usefulness in messing around with your colors here. It's one thing, it's pretty quick to go and find a new color. So what I'm going to do, probably, I have a video coming up a little bit later that's going to cover rotary encoders. And I figured rotary encoder would probably be a lot more accurate to use than a pot. So once I do the rotary encoder, I'll probably come back, add rotary encoders to the hex keypad here, and also work in the gamma correction tables. And we'll probably make a new video on this and see if there's any value in what we find out there. So anyway, thanks for watching this. Hope you enjoyed it. Hope it's a little bit useful. And we'll see you next time.